Hello, we're Team 7 studying Burj Al Arab. For this week's presentation, Oh Jung-hoon, Kong Tae-won, Woo Jin prepared research about the tower crane, V-shaped core, and ACS. Park Tae-rim provided a review of the artificial island, and lastly, Yoo Sung-woo worked on the creation of episode and second presenter. By far, for 6 weeks, we have worked on project management, the artificial island, and detailed aspects inside. From this week, we'll start our study about Burj Al Arab's main building, starting from a V-shaped core, then exoskeleton, restaurant, helipad, rooftop, and lastly, terrace. Let's begin our sixth presentation. The presentation will proceed starting from a brief review about the artificial island, then moving on to this week's episode about the shape of the core and its solution and construction of it. We'll end our presentation with a short preview about next week's story.
For a total of 3 weeks, we've looked upon Burj Al Arab artificial island. We started with 3 problems behind it. First, a clash between architecture and engineer on whether the artificial island should be built or not. Secondly, the enormous capital problem for construction. Lastly, risk factor of building a high-rise building on the artificially built island. The first and second problem was easily solved by the client power. The client strongly wanted to build the buildings on artificial island. The client was also the prime minister of a country, therefore the financing problem was solved. Solving the risk factor was important. The construction of the artificial island started with inserting tubular piles inside the seabed. Then, they erected sheet piles that would form a shape of an island and temporarily connected with the tubular piles. The inside was filled with sand and rock armors were arranged around for stabilities. Now, risk factor arises after finishing the construction until here. First was the sand. They had to build a 321 meters tall building on an unstable material. They solved this problem with skin friction, which is the friction between the surface. The piles inserted stayed stable and rigid because of this friction. The second risk factor was high waves. Lying on the major fault line, Dubai had high waves. Considering the safety, they had to follow the engineer's suggestion of raising the island height. However, to fulfill the architecture idea of the world's best hotel, instead of raising the height, they installed seawalls around the island, a classic way to decrease the power of waves. They placed shed unit, unique but efficient, and uniform breakwaters around. Third and last risk factor was the water pressure. They needed to excavate the sand for the basement. However, there was a problem. Because of water pressure difference, blindly excavating could result in boiling effect or sand boil. This was solved by jet grouting method and bottom grouting with a temporary sheathing method, which was done by constructing a slab with cement seal which could endure water pressure. This effectively prevented the water from flowing to the foundation. After that excavation was possible, with all the sand excavated, they created the concrete slab for the basement. and removing the exposed concrete piles, the artificial island was finally done. This is how the Burj Al Arab successfully built the one and only artificial island despite those various risk factors. Now, from this week, we will talk about the main building. To effectively describe the shape of a yacht, the core of the Burj Al Arab was decided in a V shape. Burj Al Arab's two unique aspects were created because of this V-shaped core. The first one is the fabric work. The front of the building, fully exposed because of the V-shaped core's two wings, was covered with the fabric work which also resembled a real shell of the yacht. Also, the center space created between the wings and the fabric work worked as an enormous atrium up to 180 meters. This atrium is where the guests of the hotel first encounter an interior of Burj Al Arab. Therefore, the client put careful effort into the design. This V-shaped core granted various characteristics to the building, making Burj Al Arab more special. But there was still a problem. It was about the direction of the building. Tom Wright wanted the building's front to face the land, while other team members wanted to face the sea. This problem was solved easily because the client wanted the front to face the land. Also, because of the wind load, it had to face the land. Dubai, located in a sweltering place, has a strong wind. Therefore, they had to consider the wind load problem, which is also a classic problem for skyscraper. If the building's front faces the sea, a large area is exposed to strong wind, endangering the building's stability. As a result, Tom Wright wanted the building to face the shore and facing the sharp part of the V to the sea. But this couldn't perfectly handle the wind problem. Then, how did they solve wind problem more specifically? Starting from this week, we will look upon Burj Al Arab core shape and the construction method, and other structure and technique to resist the wind.
This week, we'll investigate Burj Al Arab's core. For a total of 6 years of the construction period, Burj Al Arab spent almost half in constructing an artificial island. For a limited time of 3 years, they needed to finish the main building. Therefore, they needed a method to reduce the construction period. The method they chose was Core Structure Advanced Construction Method, or CSACM in short. This method starts with construction concrete at core firstly, then moving on to other parts. As the core takes up most of the area of the building, constructing core first could lead the whole process and secure the building to be built vertically straight. Also, as the core part and wing part of the V-shape was separated in construction, the workers could work with their steel, concrete, and any other fluently without distraction. They needed a way to process CSACM quickly and safely, so they chose the Auto Climbing System, which is ACS in short. ACS is a system where they use the hydraulic unit and rail to form level by level. It's also known as jumping formwork. It works firstly by attaching the anchor system to the ACS form. They place concrete at the height of the first floor to make a wall and attach an anchor shoe to the wall. Anchor shoe works as a support when the ACS form goes upward. The ACS form is connected across a total of 3 levels. Each level is completed by forming concrete with mold from both ACS form at the exterior wall and the other side. When the concrete is formed, they extend steel to the upper level and prepare to form another level. Anchor shoe is attached to the completed wall, and using the hydraulic system and climbing rail, the ACS form moves to the next level. They continue the same process again and again. It usually takes an average of 3 days to complete one level. Usually, ACS does not need tower cranes to process the system. However, Burj Al Arab used 3 cranes in total. Why did they need so many cranes? It was because of its unique structure. The first unique structure was the exoskeleton, which we will be studying next week. The hotel is covered with various steel structures. These steel structures weigh up to 60 tons each. To move and erect them at the right place, they needed cranes. Also, Burj Al Arab is known to have only 28 floors despite its height being 321 meters. It's because every room has mezzanine, making the floor height of one level up to 7 meters. Cranes worked crucial parts in creating this double-layer room. 3 cranes consist of one main crane, which is located at the core part, and 2 sub-cranes at the wing part. When building a low building, cranes are situated in the outer part of the building, but for a high-rise building, the cranes should be located above the building. How did they install the cranes, and how do they work? D tower section with a hydraulic system is installed at the foundation. Above it, IC tower section is installed, and then B tower section. Then the IC tower section is installed again. When the building is constructed up to the crane's highest point, they fix the ladder placed at the left and right part down to the low D tower section. Then using the hydraulic system, the crane is moved upward. They continue this process along with the height of the building. As using the CSACM, the core was constructed in advance. Therefore, the main crane was placed a little higher than the outer wing's sub-cranes. Starting from the foundation we've completed last week, using the auto-climbing system, the core is built in advance, 2 wings following. ACS creates a one level in approximately 3 days. The 2 sub-cranes at the wing part are used to install the mezzanine slab of each room. The slab for the mezzanine was formed uniformly by prefabrication. When the 7 meters high floor was completed, then the slab is installed. This is how Burj Al Arab constructed the main core and double-layer room. However, the problem with the wind load was not over. Next time, we'll study what structures were applied to make the building more stable from the wind load. Thank you for listening.